Hi, my name is John Hunt. I'm a consultant to the Federal Highway Administration on transportation hydraulic engineering. I've got over 30 years experience in the field, and I'm also an instructor in the National Highway Institute's training courses on transportation hydraulics. We put together this video to give you some ideas and provide an example of field scoping for a bridge hydraulics study or design. The focus of this video is going to be on the field portion, but there's a lot that you can do in the office. Think of it as office reconnaissance prior to going out in the field that will really help you to be more efficient and get more insightful information when you're in the field. So let's take a look at that. You can learn a lot about the crossing site and the river reach using some really helpful online resources. Here, we're using an aerial imagery application, and we're going to use it to get more familiar with the site. So let's zoom in on the project area. And let's say we want to do a hydraulic study and design for the replacement of this crossing. You've got the road here and the bridge. We can see the river channel and the adjacent land use and ground cover. We can look as far upstream or as far downstream as we want to. And by the way, in this example, the flow is from northwest to southeast. We're going to start by looking at the channel alignment. So imagine that you're in a raft and you're floating downriver, starting here. You go through this bend to the right, and then immediately into a bend to the left. And in that bend to the left, you've got the bridge site. And what's happening downstream? Well, the channel splits in two to get around this mid-channel bar. And downstream of that, what is this? It's a diversion structure. It's essentially a low dam across the channel, and it causes weir flow conditions for this low flow, but also even for flood conditions, we can expect that this will become a critical depth control section. And that means that it makes it a really good candidate for the downstream end of our hydraulic model, whether it be a 1D or 2D model. Well, also, we can get a look at the terrain. So let's get an oblique view. Now we're looking downstream with an oblique view. The bridge site is right there. And this hillside to the right, that's essentially the south edge or right edge of the floodplain. So it's obvious that in flood flow conditions, this terrain feature is going to have an effect on the hydraulics. Now, a really great thing you can do here, the Federal Emergency Management Agency, FEMA, has created something called the National Flood Hazard Layer. You can go to their webpage and download that layer. And when you do, you can plot the flood inundation here on this image. And that's what we've got here. These shaded zones, that represents the floodplain according to FEMA for this reach of the river. And really any reach of any river that's in a FEMA regulated floodplain, you should be able to get this data for. Well, we've just barely scratched the surface of the things you can do, but as you can see, you can accomplish a lot of pre-field reconnaissance using an application like this one. Before you go to the field, you want to anticipate some of the major design considerations. Most bridge projects have regulatory constraints or permit requirements that are going to need some hydraulics input. For instance, you might need a floodplain development permit, and you'll need to know what agency at the state or local level has the authority to issue that permit. The example we showed you before, that was a crossing over a FEMA floodplain, and in that case, the county would issue the permit. You should engage the environmental experts in your agency to find out if there's a way on this project to provide some environmental enhancement, maybe some in-channel or riparian habitat improvements that will complement the project. Other design considerations you will look into will have to do with the hydraulic capacity of the crossing in the floodplain, how you want to model it, and stability issues. And you can use aerial imagery, like we did with the application we were looking at earlier, to develop these considerations. So for instance, hydraulic controls. You want to find out, are there any that are visible, whether they're structures across the channel or structures in the floodplain? What about if we want to calibrate, which we should try to, we want to know if there are recent past floods and did they leave behind high water marks? Is the crossing skewed, meaning not perpendicular to the flow? What about ice and debris? Are those causing issues for maintenance? And is there any data that suggests that there are stability problems with the channel, either laterally or vertically? Examining these things before you go into the field will inform you as to what things you need to look at and look for when you're in the field. Another pre-field activity is gathering as much information as you can about the existing bridge, and of course that includes as-built plans. Take a copy of these with you into the field and verify the span lengths. Do the piers look like in the field what they look like on the as-built plans? If the as-built plans show countermeasures, can you still see those in the field? Have things been added since the original construction that don't show up on the as-built? Also, the as-built show you things that are underground that you can't see in the field, like these spread footings and the elevations of the spread footings. There's great information for you in the bridge inspection reports. Now, these item numbers and the code values are subject to change, but as of right now, a code of 3 under item 113 tells us that this bridge is scour critical. Items 61 and 71 in the current coding guide are also important because item 61, for instance, that code 6 tells us that the inspectors found a problem with the channel bank protection, or there's some minor stream bed movement that's evident. This code of 9 under waterway adequacy, that tells us that in the inspector's opinion, there is the chance of roadway or bridge deck overtopping in a flood is remote. Also in the bridge inspection reports, look for this. It's the measurement of the stream bed elevation at the bridge faces, ideally at different points in time. And you can see if there's a trend towards channel lowering, which is degradation, or the channel increasing in elevation over time, and that's aggradation. Well, once you've got your pre-field reconnaissance done and you're ready to head into the field, make sure you've got all the equipment that you need. That includes safety equipment, of course, and also that you've got appropriate forms that are going to help you to be as efficient as possible in the field. And to help you with this, the FHWA has produced another video in the series with the title, Data Mining and Preparation for Project Field Scoping. Please refer to that video. And now, let's get outside. In this portion of the video, we're going over what you're going to want to look at and document when you're doing the field reconnaissance for a typical bridge project. Now, this could be a bridge replacement, it could be a new bridge where there is no existing bridge, or it could be for the evaluation of scour at an existing bridge. The observations that we take from this field visit are going to help us make an appropriate and accurate hydraulic model, and also provide information and insight that are going to be needed in the design of the bridge. Here we're standing a pretty good distance upstream of the bridge. I'm looking down at where the bridge is, so you're looking upstream, and I'm standing at the left bank of the river. When we say left and right, we're talking about as if you were looking downstream. So I'm at the left bank of the river, and we can see that this portion of the river is in a bend. This left bank is at the outside of the bend. Across the channel, you see this point bar, and that is basically sediment building up that builds up at the inside of a bend. It's a natural process. And that same process that's building the bar on the inside of the bend is working to erode this left bank, or trying to, which is at the outside of the bend. And you can see that this bank on the left side is pretty steep. It's been undergoing erosion, but I can also see, looking down at the lower portion of the bank, that there is some bank protection in the form of rock riprap that is trying to hold that erosion. Now, if we're doing a one-dimensional model of this stretch of the river, then we're going to be talking about cross sections. What would a cross section of the flow look like? Well, as we look across the channel here, number one, we can see that this channel is pretty deep. The channel will carry quite a bit of flow before it starts going out, before the flow starts going out into the floodplain. Over on the right floodplain, that looks pretty high. It's hard to tell how much flow would be carried in the right portion of the cross section because it is pretty high compared to the left side. Over here we have the left overbank portion of the floodplain, and it's pretty wide and it's also pretty clear. It's going to be carrying a lot of flow in the left overbank of, say, a large flood like the 100-year flood at this point. But also at this point, this is where the flow would have to start contracting to get through the bridge, because not far downstream from here we have the road embankment, and that road embankment, unless the flow we're interested in would overtop the road, but assuming it doesn't overtop the road, that flow has to contract to get through the bridge opening. And so downstream of this point, the two overbanks, the left and right, will begin to become less and less effective in carrying flow downstream. That concept is called ineffective flow, and we're going to talk more about that a little later on in this video. Now, this field reconnaissance is really your best opportunity to get a good handle on what the roughness values should be, your Manning N values for your model cross sections, or if it's a 2D model, then the N values you're going to assign to the elements. And so let's just see what we can see about roughness here. I'm going to start with the bottom of the main channel, and as I look downstream from here, the bottom of the main channel is pretty smooth. There's smooth cobbles and gravel on the bottom, not a lot of obstructions or undulations. And so I would call that an N value of about 0.025, maybe as high as 0.03. But behind me, which is further upstream, we see these boulders sticking up, and they're going to add a little more roughness. In that portion, the bottom of the main channel might be more like 0.04. So that's the bottom of the main channel, and of course that's unvegetated. Now we're going to start looking at areas that will have varying degrees of vegetation. That point bar over there, which we've talked about before, it doesn't have any vegetation on it because it's fairly new. That again is going to have those same low N values, the 0.025 to 0.03. But you can see a vegetated area behind or to the right of the point bar, and we're here in January, so all the leaves are off and you can't really see much of the undergrowth. But if we were here in the summer, which is really our flood season here, you'd see a lot of undergrowth there, and it's really pretty dense vegetation. So in that area that's covered by that vegetation, I'm going to want to assign an N value that's maybe 0.08 to as high as 0.12. Looking over here on the left bank, well, it's a different kind of vegetation, isn't it? There's grass and weeds, but there's not really anything that's substantial that would stand up and resist the flow. So this left bank is pretty smooth. I'd say 0.04, 0.05 at the max. And then if we're looking at the left overbank area, well, we do have scattered trees. In fact, the overbank does go as far as those big trees you see over there to the right of the bathroom facility, but those are just isolated. In general, the roughness of this left overbank is pretty low because of the type of vegetation we see. Again, in the summer, it would look different. But this is basically grasses and weeds and sedges. I'm going to say this is 0.05, maybe as high as 0.06 in the left overbank. So that's basically how you capture information about the roughness. And of course, you want to take a lot of photographs at all of these vantage points. So here at this point, you want to take a photograph of what your overbanks look like on both sides, photograph of the main channel, so you're capturing the roughness characteristics there and capturing that sense of deepness to the main channel. Well, now we're standing just a little ways upstream of the bridge. I'm standing in the river bottom, really. If this were during spring runoff, if I were standing here, I'd have to be in waders. But we're here to look at the bridge opening itself and talk about the effects that the bridge will have on the hydraulics of this river reach. So we can start at the far right end, the right end of the bridge. We call that the right abutment. Now, this abutment is a vertical wall, a really tall one, with a wing wall, with wing walls on both sides, really. And the vertical wall comes up from the bottom of the channel bank slope. Well, what that means is that flow in the main channel, if we had a flood that was large enough to fill this main channel, well, on the right side there'd be a triangular wedge of obstruction formed by that vertical abutment wall that's coming up out of the bottom of the channel bank slope. Next, we can look at the pier. This is a two-span bridge, so we just have the one pier in the center. It's what we call a wall pier, in that it's continuous from the upstream end to the downstream end, and it's got a rounded nose, which is much better than if it were a squared off nose. Now, for flow that's strictly contained in the channel, for what I should say is for channel flows, the pier looks to be pretty well aligned with the flow. But it's not so easy to tell here, but this is actually within a bend. Now we're at the inside of the bend here on the left bank, and the right bank is at the outside of the bend. And when you look at aerial imagery as to how the floodplain is configured here, it's easy to imagine that during a flood flow condition, the flood flows would probably attack that pier at more of a skew. Rather than head on, there would be a bit of a skew angle for the pier, and that's going to affect the hydraulics as well. Well, we can only see a portion of the left abutment from here, but if you could see the upstream side, you'd see that it's built the same way as the right abutment in terms of being a vertical wall coming up from the bottom of the channel bank, forming again a wedge of obstruction to the flow that's along the left bank. I also want to look at the bridge superstructure, the bridge deck itself. Now, the bottom part, the bottom line of the superstructure, we call that the low chord. And on this bridge, that's pretty high up. I can imagine it would take a lot of flow, a very large flood, to get to where that low chord was submerged by the flow. If it was, that would be called pressure flow. Pressure flow is a condition that really causes a big impact on the hydraulics. I am guessing that even in a 100-year flood, we would not reach pressure flow at this bridge. Now, our hydraulic model will either confirm or refute that statement, but my guess at this point is that it's high enough to be out of the 100-year flood. So, another thing we would want to think about, if we thought the bridge deck was going to overtop, we would need to look at the rail and ask ourselves, well, is the top of the rail really the control on overtopping flow, or is it the top of the concrete bridge deck? In this case, that rail is pretty open. So my guess is that the way I would model it would be to have overtopping begin not at the top of the rail, but at the top of the concrete deck. One of the things you need to think about when you're doing field reconnaissance for a bridge project, you're going to be doing scour calculations. And for contraction scour, that can either be a live bed or a clear water contraction scour equation. Well, how do you know which one of those it is? The answer to the question is based on here at a point upstream of the bridge, a significant distance upstream of the bridge, the main channel flows during a flood. Now again, this is a very low flow condition. The flow would be where I'm standing and a lot wider than this, and it'd be a lot deeper than what we see now. The question is, in a big flood like that, would the velocity of flow be fast enough to pick up this bed material and move it downstream into the bridge opening? The hydraulic modeling is going to be needed to really answer that question. At this point, we're just making a qualitative assessment of it. Well, this is very coarse bed material. It's gravel. You can see cobbles, 3 to 6 inch, even some 8-inch cobbles. It's going to take a high velocity to pick this up. Now, one thing I'll mention is that this particular stream reach, this is an armored bed. If I took a shovel and dug down a foot to 2 feet, well, even less than that, I would get into a much finer material. Underneath these cobbles, we'd be more in a gravel situation. So really an assessment you have to make at a site like this is, would the flows be high enough to move this armor layer out of the way and get down to the finer bed material that's underneath? And if the answer to that is yes, then this would likely be a live bed contraction scour situation. And if the model tells us no, that velocity is not going to be high enough to move this armor layer, then we'll really have a clear water contraction scour situation inside the bridge. Where I'm standing now is right upstream of the road embankment. The bridge is that direction from me, but I'm to the left of the bridge. I'm in the left floodplain, and I want to talk about visualizing the flow conditions in the floodplain in the vicinity of a bridge. So off in that direction, that's the left overbank, the left portion of the floodplain. And further upstream, it's going to be carrying a lot of flow. And even right here where I'm standing, there is going to be water here. It could be pretty deep, could be up to my shoulders, a pretty deep stand of water. However, in this location, it's not actively flowing downstream. And you know why? Well, it's because that road embankment is preventing that from happening. Because of the road embankment, unless the flow is able to overtop the road, which in this location, the FEMA floodplain mapping says it wouldn't. But so unless it's overtopping the road, then the flow here, if it's moving at all, it has to be moving in this direction towards the bridge. So that means it's not being effectively carried downstream. So you have to visualize that and incorporate that. If you're doing a one-dimensional hydraulic model, you incorporate that idea as what we call ineffective flow, because there's a large portion of this left overbank that's not effective for carrying flow downstream, because the flow here has to be moving towards the bridge, which is lateral and not downstream. And by the way, this is a good time to plug two-dimensional modeling, because if you use a two-dimensional modeling, you don't have to imagine the ineffective flow and make guesses as to what that flow pattern looks like, because a two-dimensional model will actually directly compute it for you. When you're here at the bridge during your field reconnaissance, you have a chance to look for signs of scour. Well, at this pier here, you can see a little dip in the ground against the side of the pier at the upstream nose of the pier. It's pretty clear to me that that is a remnant of a pier scour hole. It's important to realize, though, when you're in the field looking for signs of scour, we did have a big flood here 6 years ago. It would be a mistake to think that that is how deep the scour got during that flood. It probably got a lot deeper at that location. But what happens in live bed conditions, if indeed this was live bed, is that after the peak of the flood has gone by and you're now in the receding part of the flood, towards the end of the flood, the material infills the scour hole. So what we're seeing here is what's left of a scour hole that at one point was a lot deeper, and then it got infilled by the lower flows at the end of the flood. But this does show you that scour can be generated at the upstream nose of that pier. Now we can look here at the left abutment. Now, as I've been talking about the flows in the left overbank being prevented from going across the road by the embankment, meaning that the flows have to come through the bridge, well, that concentrates a high velocity and very turbulent flow here at the abutment. You can see the riprap that they've put at the upstream corner of the abutment. Now, it's interesting that it stops where it does, but this is indicating to me that the bridge owner has experienced scour problems at that abutment and has decided to prevent further or later formation of scour by putting that riprap there. Now normally at a bridge abutment, we would expect to see that protection carrying all the way along the length of the abutment wall and wrapping around the downstream corner in a similar fashion to what it does here. It's unusual to see it stop here. And at first that could cause me some concern because there's not riprap where I expect to see it. However, there's something to point out. There was a big flood here 6 years ago, and that tree was no doubt standing there 6 years ago, and there wasn't enough scour to affect that tree or to rip it out of the ground. So that is a clue that the scour conditions must not be that bad at this abutment in a flood condition. Not only that, there's another smaller tree that's probably over 6 years old at the downstream corner of the abutment. So that's an interesting sign that we probably don't have really bad scour conditions at this abutment. And now we've moved to a vantage point downstream of the bridge because there's a lot of information we need to gather about the conditions on the downstream side. So first we can look up at the bridge, and now this could get confusing because we're looking upstream. And I'm going to talk about the right abutment, which we can see, but it's to our left. So that's the right abutment. We can see how that looks from the downstream side. Now we're seeing almost the full length of the pier. We've got the downstream nose of it. Something that's worth pointing out here is that I mentioned before that the bridge was in a bend and that the left side is the inside of the bend. And what I didn't mention before is that there's a point bar coming off from the left bank because it's at the inside of a bend. And that point bar extends throughout the whole length of the left span of the bridge. It extends all the way out to the pier in the middle. And so that, of course, slightly affects the capacity of that span. We can see that we've got a lot of vegetation on both the right and left bank. It's heavy vegetation on the bank slopes. Again, if we were here during the summer, which is really the flood season for this area, we'd see a lot of undergrowth and that this is pretty thick vegetation. So again, I'm going to say N values on the order of 0.08 to 0.12 here. Now, that same thing applies to the left bank. We've got the same kind of vegetation over there. Because the right bank is at the outside of a bend, we see that there's a lot of places where the bank is nearly vertical and in some cases undercut. We see places where bank protection has been placed along there. Some of it formal, but most of it kind of an informal placement of bank protection. We don't know how well that would stand up to a really large flood, although again, we can say we know that this flood 6 years ago was pretty heavy, and this bank protection seemed to sustain that. Something really important to point out, I think, here is that we are located near the upstream end of a mid-channel bar. We can see the mid-channel bar extending further upstream from where we're at. Again, this is downstream of the bridge. Now, a mid-channel bar, that's an aggradational feature. That means that there's been deposition that has occurred in this reach. Whether it's still ongoing deposition or not, or if it's more historic, we don't know until we do further investigation from various data sources. But we know that it has aggraded here, and we can look at the N values in the channel. These channel N values again are going to be fairly low, on the order of 0.025 to 0.03. We notice that we have some woody debris that's been at some point deposited onto this mid-channel bar. That's not surprising. Woody debris during a flood tends to flow along the center of the channel. And if we get to an area where the velocity is lower or the depths are shallower, we could expect to see debris hang up there on a bar like this. And so that's not very surprising, but it's something to note. Now, when we were upstream of the bridge, I didn't notice any debris laying in the channel upstream, and that's a good sign, because you don't want to have a lot of potential for debris to hang up on the bridge pier. Being downstream, we don't expect this debris to cause any significant problem for the bridge. Now we're in the same location, but our focus is downstream instead of upstream towards the bridge. So why is it important to be downstream of the bridge and looking downstream? It's because in hydraulic modeling, you need to have a good handle on downstream conditions because of the effect that they can have on the water surface profile through the bridge reach, and even to an extent the stability through the bridge reach. Now, I want to focus on this mid-channel bar. We mentioned it before. Here we're seeing the downstream extent of it. It's big, and from the vegetation we can see that it's been here for quite a long time. And again, this is an aggradational feature. But something that happens with the formation of a mid-channel bar, it puts added stress on the left and right riverbanks. So if we look over there at the left bank, we see undercutting and vertical banks. You see exposed tree roots, and that just shows us that this bank has been eroding. There's also been informal attempts at holding the bank with stone and rubble that don't seem to be working very well. So these are things we need to notice when we're downstream of the bridge. This mid-channel bar with all of its vegetation puts a lot of roughness in the main channel portion of your cross section. So this is going to be a 0.08 to 0.12 or higher end value region right here, with the two parts of your main channel with their much lower end values off to the side. Now, by the way, looking back at that debris or the exposed tree roots on the left bank, something I should mention is if we saw that upstream of the bridge, we would have to be concerned that this was going to be a source of debris in future floods, that these trees could get undermined completely, fall into the stream, and then get hung up on the bridge. But thankfully, these are downstream of the bridge and not upstream. Now, you remember that you need to take a lot of photographs during this field reconnaissance. You're going to be glad for all the photographs that you took when you get back to the office. So for instance, here from this location downstream of the bridge, you'll take a photo upstream towards the downstream face of the bridge and downstream towards what'll be the downstream end of your model. Now, we've mentioned stream stability issues a lot during this video, but only briefly. And so there's a FHWA video on channel assessment that also features this same stream reach. And a lot of these stability issues will be discussed in more detail in that video. Well, thank you for taking the time to watch this video on field reconnaissance for hydraulic analysis and design of bridges.